Again, the important thing is this. When I think of 5 divided by 3, when I think of the ordered pair 2, 3, I do not have to think of a picture. I can think of these things analytically, but the picture gives me certain insights that will help me with my intuition and aid that I don't want to relinquish. For example, going back to the graph again, thinking of the analytic term greater than, notice how much easier it is to think of, for example, higher than. See one point being higher than another, or to the right of. You see geometric concepts to name analytic statements, or instead of increasing, as we mentioned before, to say rising. And there will be many, many more such identifications as we go along with our course. At any rate, let's continue to see then what is the relationship then between functions that we talked about and graphs. The idea is something like this. Let's return to our friend of the first lecture, s equals 16t squared. We can think of a distance machine being the function, where the input will be time, and the output will be what? The square of the input multiplied by 16. Observe that from this, I do not have to have any picture to understand what's happening here. Namely, I can measure an input, measure an output, and observe analytically what is happening. However, as we saw last time, our graph sort of shows us at a glance what seems to be happening, that we can identify rising and falling with increasing and decreasing, and things of this type. We will explore this, of course, in much more detail as we continue in our course. By the way, there's no reason why the input has to be a single number. For example, why couldn't the input be an ordered pair of numbers? Among other things, let's take a simple geometric example. Consider, for example, finding the volume of a cylinder in terms of the radius of its base and the height. We know from solid geometry that the volume is pi r squared h. We can therefore think of a volume machine where the input is the ordered pair r comma h, and the output is the single number pi r squared h. And by the way, notice here the meaning of ordered pair. You see, if the pair 2, 3 goes into the machine, notice that the recipe here says what? You square the first member of the pair. In other words, if 2, 3 is the input, we square 2, which is 4, multiply by 3, which is 12, and 12 times pi, of course, is 12 pi. On the other hand, if the input is 3, 2, the first member is 3, our recipe squares the first member, that would be 9, times 2 is 18, times pi is 18 pi. But again, observe that I at no time needed a picture to visualize what was happening here. Of course, if I wanted a picture, I could try to plot this also, but notice now that my graph would probably need 3 dimensions to draw. And why would it need 3 dimensions? Well, notice that my input has 2 independent measurements, r and h. And therefore, I would need 2 dimensions just to take care of r and h. Then I would need a 3rd dimension to plot v. And by the way, notice the next stage. If I had an input that consisted of 3 independent measurements, this would still make sense, but now I would be at a loss for the picture. In other words, what I'm trying to bring out next is the fact that whereas pictures are a tremendous help, maybe a second subtitle to our lecture should have been, "A picture is worth 1,000 words, provided you can draw it." Because you see, if we needed 3 independent dimensions to locate the input, and then a 4th one to locate the output, how would we draw the picture?